We're going to finish up our review of general chemistry in chapter 1 with a discussion about bond length and strength and polarity and how to identify polar molecules and nonpolar molecules. So I just want to remind you that as the number of electrons between two nuclei increase, bonds become shorter and stronger. Okay? And so what we find here, and there's a couple ways for you to look at this and think about it, right, is if you are more of a kind of a diagram person, right, what we see here is bond length increases as we go from triple to double to single bonds, and then bond strength increases as we go from single to double to triple bonds. So that those are inverse, right? They're inversely proportional to each other. If you're more of a numbers person, I find this table is really helpful to visualize this. We're comparing carbon-carbon single bonds to carbon-carbon double bonds to carbon-carbon triple bonds. And what we find here is that here are the measured bond lengths, and so we can see how they increase. And then here are the bond strengths, and we can see how these increase. Now, I want to talk for just a moment about double bonds. When we talk about double bonds, right, remember we have a pi bond and a sigma bond. Double bonds are still quite strong, but remember the pi bond is a little weaker than the sigma bond, and we'll talk about that more in chapter 10. Let's also look at carbon-hydrogen bonds. So when we come over here to look at carbon-hydrogen bonds, what we find is the length and the strength of a carbon-hydrogen bond here, here, and here varies depending on the hybridization of the carbon atom. And so to understand why, we need to look at the atomic orbitals used to form each type of hybrid orbital here. And so one of the things I want to review, we talked about this in a previous screencast, but when you have an sp hybrid orbital, it has 50% s character. It's made of 1 2s orbitals, right, out of 2 hybrid orbital. So like, if you think about it, it's 1 2s orbital for 1 p orbital. Then if you have an sp2, you have 1 2s orbital out of 3 hybrid orbitals. You've got an s and 2p, and that gives you 33% s character. And then an sp3 gives you 25% character. And so what we see here is when we have an increased percent s character, we get an increased bond strength and a decreased bond length. And so maybe the burning question in your heart is why? And that's a great question. Why does the percent s character affect the length of the carbon-hydrogen bond? What's going on there? Why are we seeing that? Well, a 2s orbital keeps electron density closer to a nucleus, or to the nucleus, compared to a 2p orbital, right? So as that s character increases, the hybrid orbital holds its electrons closer to the nucleus, and that means that bond becomes shorter and stronger. Now, let's talk about electronegativity. So electronegativity is just a measure of an atom's attraction for electrons in a bond. And we talked about this when we were talking about Lewis structures. And so just as a brief review, right, this electronegativity increases as we go across a period from left to right on the periodic table. And this increases as nuclear charge increases. Right? And then we see there's increasing electronegativity as you go up a column, right, or up a group, and that occurs as the atomic radius decreases, bringing valence electrons closer to the nucleus. Right? So when we talk about electronegativity, I kind of view it as it just indicates how much an atom wants an electron, right? And fluorine there wants an electron more than anybody else on the periodic table. Okay? So let's talk then. So electronegativity helps us predict bond polarity, which helps us predict whether molecules are polar or not, which helps us predict a plethora of physical properties about the molecules. Okay, and so let's talk about bond polarity. So basically what we see is that electronegativity values are used to indicate whether the electrons in a bond are shared equally. And remember, when something is shared, when those electrons are shared equally, that's a nonpolar bond, or unequally, which would be a polar bond between atoms. Okay, so if these are shared, I wrote equally, shared equally. So I wrote equally twice. So let's get rid of one of those. So if they're shared equally, then we say the bond is nonpolar. Or if we say they are shared unequally, we say, look, that bond is polar. And you're only going to see bond polarity in covalent molecules. So sometimes you'll hear like, oh, this is a polar covalent, right? Or nonpolar covalent. So you'll see those pop up pretty frequently. Let's look at a nonpolar bond. So a carbon-carbon bond is a nonpolar bond. The electronegativity values of carbon are 2.5, and so the difference between them is 0. And so because there's no difference here, it's a nonpolar bond. Whenever you have different atoms, but they have similar electronegativities, where the difference is approximately 0.4 or less, then that's a nonpolar bond. Carbon and hydrogen here, that difference is 0.3. If we take 2.5 and subtract 2.2, that's 0.3. And so it is classified as a nonpolar bond. So that's just kind of a, most of what we're going to deal with in organic chemistry are carbon-carbon bonds and carbon-hydrogen bonds. And so it's helpful to understand that if you have a molecule that's just carbon and hydrogen, there's not a big enough polarity difference for it to be a polar molecule. It's going to be nonpolar. Now, we are going to also look at some heteroatoms. And when you do introduce heteroatoms, you introduce a bigger difference in the electronegativity, and that results in polar bonds. And polar bonds are kind of where it's at, right? That's where we get some really interesting reactivity. So when you have bonding between atoms of different electronegativity values, and it results in an unequal sharing of electrons, that is a polar bond. And so here is an example of a polar bond. We have carbon and we have oxygen. Now, you don't have to memorize the polarity values. You just need to understand the trend. And you can say, hey, look, I know on the periodic table, carbon is like right here, and then we have nitrogen, and then we have oxygen, and those are pretty separate on the periodic table. So oxygen is going to be more electronegative than carbon. And so that means, right, the electrons are pulled from the carbon towards the oxygen, that element of higher electronegativity. So the bond is polar or polar covalent, and the bond is also said to have a bond dipole. And all that means, right, is that you have a separation of charge. Now, recognizing this is critically important in organic chemistry because we know that things that are positive like things that are negative. And so being able to identify things that are electron deficient and electron rich are going to help you predict the reactivity of molecules. So if you are sitting there and you're saying, oh, I didn't like this in Gen Chem and it's back again and I don't really understand it, maybe I can just gloss over it and get through, I really want to encourage you to please come to my office and let's get a really great grasp of polar bonds and identifying molecules that are electron deficient and electron rich. So when we talk about this, right, I want you to notice a few things. You've got a delta positive there. That's a lowercase delta, and that it's written kind of like the squiggly S here, so kind of like a fancy S, and that means that atom is electron deficient. Right? Sometimes it's even referred to in some books as partially positive, right? So you'll hear me talk about that. And then you can also have things that have the delta negative here. This is the more electronegative atom, right? And that atom is electron rich, okay? And so the direction of the polarity in the bond is indicated by an arrow here, with the head of the arrow pointing towards the more electronegative atom. The way I remember it is you start with this fun little positive here, and that's when you start there, that's that partially positive atom, right? And you point towards the thing that's more electronegative. And that's just showing you, hey, look, those electrons are held more on that oxygen, making it partially negative. So we've been talking about bonds, right? And how we know that bonds themselves are polar bonds or nonpolar bonds. But now we want to talk about molecules, because you can have polar bonds in a nonpolar molecule. So I want to show you an example of that. So here is carbon dioxide. This is a nonpolar molecule, right? And it has polar bonds. We just spent a lot of time talking about how carbon and oxygen here, that's a polar bond. But what you see is there's symmetry in this molecule. And the dipole pulls this way and the other one pulls this way. And it's like a tug of war where you have two people with equal strengths on either side. And so they cancel each other out. And so this whole molecule is a nonpolar molecule. So a nonpolar molecule, right, either has no polar bonds, right, or two or more bond dipoles that cancel out. Right? And so carbon dioxide is a really great example of that. It's a linear molecule. The two dipoles are equal and opposite in direction, and so that means they cancel. When you're starting, I think it's a lot easier to recognize nonpolar molecules than polar molecules when they are small, okay? So for small molecules, what we see here is if it's all carbon and hydrogen, we are nonpolar, right? If it's all carbon and hydrogen, that's a nonpolar molecule. If it's the same element, for example, your halogens are diatomic, right? Cl2 in the gas state, F2, Br2, those are nonpolar molecules, right? Or if there's symmetry, right? And so that's why knowing Lewis structures is so important, is because it can help you visualize if there's symmetry in the molecule. So, for example, if we had CCl4, this is carbon tetrachloride, which is a common solvent in organic chemistry, and you do the Lewis structure of that, you see, hey, look, there are dipoles, right? They go this way, and this way, and this way, but they all cancel out. There's symmetry in that molecule. So then that molecule is nonpolar. So when you're trying to figure out if something's polar or nonpolar, my suggestion is to draw the Lewis structure first, analyze whether the bonds there have a difference in electronegativity, and then look at the overall symmetry. A polar molecule, on the other hand, right? If we look to your right at water, that's a polar molecule, right? It either has a polar bond, or two or more bond dipoles that reinforce each other. All right. So I want us to look at water here. This is the Lewis structure of water. Oxygen is more electronegative than hydrogen. So there are individual dipoles here where these hydrogens are electropositive, and then this oxygen is electronegative. And what we see is that this overall molecule has a net dipole. And because it has a net dipole, it is a polar molecule. Now, for small molecules like water, if there are electrons on the central atom, then we can kind of automatically say it's going to be polar, right? If we've got lone pair electrons here. Now, once you get into larger organic molecules and larger biochemical molecules, that falls apart because you have to weigh the amount of carbon versus the amount of oxygen. But for your small molecules, it's a really nice shortcut. Let's do an example, right? We've got two molecules here, and it says, is the molecule polar or nonpolar? And if it's polar, show the direction of the dipole. The first step when you're solving this problem is to draw the Lewis structure. So you can count the valence electrons. I'm going to go ahead and draw the Lewis structure for us. And remember, Lewis structures are two-dimensional molecules, and so sometimes we can draw them like this, right? And that's not a great representation when we're talking about dipoles. And so that's where we really need to remember that this is got a structure that looks a little bit more like that, okay? And so when we look at this, the first thing, after we draw the Lewis structure, we need to compare the electronegativities. We know fluorine is much more electronegative than boron. And so we are going to see the dipoles move that way, right? And what we see here is because the fluorines here have the same electronegativities, we're all pulling the electrons with the same strength. And so all of those cancel. So this has no net dipole and is a nonpolar molecule. So that's how we can figure out that's a nonpolar molecule. Let's look at ammonia. When we draw the Lewis structure, it looks like that. It's a small molecule, and so it's got lone pairs on it. So kind of an easy shortcut is, hey, that's going to be polar. But what we can do is go through those same steps where we look at nitrogen and hydrogen. We see there's electronegativity difference there. And so we say, all right, that means that nitrogen is going to be partially negative. This is going to be partially positive. And so the direction of the dipole is going to kind of head towards that nitrogen there. And so that means that this is a polar molecule, and then the net dipole goes in that direction. All right, so this finishes up for us chapter 1. Lots of Gen Chem review. There is no judgment here. So if it's been a minute since you've had Gen Chem and you have questions, or maybe you just never really understood it in Gen Chem, these are all topics that are going to come up again in organic chemistry. And so I really want you to be successful. And so if you need help, stop by my office. I'm happy to help. And we can go over all of these things.